Lecture 21, The Mathematics of Strain. To understand the mathematics of strain, let's look at this example from Allmendinger et al. Carson City and Salt Lake City are located on opposite sides of the Basin and Range Province in the western United States. The two cities are presently located 670 kilometers apart, but before extension occurred in the Basin and Range Province, they were only 335 kilometers apart. You can think of there being two different coordinate systems in this example, both of which have their origin at Carson City. We will refer to the axis before extension with a capital X, and the present-day axis with a small x. The relation between the small x and capital X axes can be described in terms of a coordinate transformation. This relates two different states in time, one in the present and another in the past. The first equation gives a point's position in present-day coordinates as a function of its position prior to the start of the extension. Salt Lake City started out 335 kilometers from Carson City and, by this equation, it should now be 670 kilometers away. This equation is called a Green transformation. It gives the new position of the point in terms of its old position. The second equation gives the position of a point in the past, given its present position. Austin City is today 240 kilometers from Carson City and, by this equation, it was 120 kilometers from Carson City before the extension. This equation is called a Cauchy transformation. It gives the old position of the point in terms of its new position. The coordinate transformations are not constant, but depend on the position of the point. However, their gradients as indicated by these two equations are constant. These are called the deformation gradients. The first equation is the Green deformation gradient, and the second equation is the Cauchy deformation gradient. What do these gradients correspond to? Delta small x gives the present, or final length between 2 points along the line, Salt Lake and Austin for example. Delta capital X is the initial length between the same 2 points. Thus, the Green and Cauchy deformation gradients are nothing more than the stretches referred to the initial and the final states, respectively. Another way to look at this problem is to consider the displacement vectors that connect the initial and final position of the points along the line. These displacement vectors are shown here for the cities of Salt Lake and Austin. And they are calculated in these two equations. In both cases, the vector, u, is equal to the initial position of the city, and it is also equal to half the final position of the city. The first equation is known as the Lagrangian displacement, which gives the displacement in terms of the old coordinates. The second equation is known as the Eulerian displacement, which gives the displacement in terms of the new coordinates. Like the coordinate transformation, the displacement vectors are not constant but depend on the position of the point. However, the change of displacement with position, or displacement gradient, is constant. The first equation is known as the Lagrangian displacement gradient, and the second equation is known as the Eulerian displacement gradient. The physical meaning of these displacement gradients becomes obvious when we expand them for Salt Lake City, here denoted by S, and Austin City, here denoted by A. Delta U is the final distance between these two cities, LF, minus their distance before extension, LI. Thus, the Lagrangian and Eulerian displacement gradients are just the elongations referred to the initial and final states, respectively. This table summarizes what we have learned so far. Transforming from the initial to the final coordinates is possible via the Green deformation gradient. And transforming from the final to the initial coordinates is possible via the Cauchy deformation gradient. Describing displacement as function of initial coordinates is possible via the Lagrangian displacement gradient. And expressing displacement as function of final coordinates is possible via the Eulerian displacement gradient. We can extend these findings to 3 dimensions. In this case, we have 3 orthogonal axes, and in the equations, the indexes I and j can have values of 1, 2, or 3. In all equations, I is the fixed index, and j is the dummy index. Also, the deformation gradients are referred to as f and f bar, and the displacement gradients as e and e bar. F bar, e, and e bar are second-order tensors. In fact, in lecture 19, we called the tensor f the deformation matrix. We'll use this table next lecture. But what is a tensor? A tensor is any physical quantity which is independent of a particular coordinate system. The physical entities of structural geology are tensors. In fact, we already looked at tensors of rank 0 and 1. Tensors of rank 0 are called scalars, and they are single numbers independent of the coordinate system. Mass, volume, density, and temperature are scalars. Tensors of rank 1 are called vectors. They have a magnitude and direction, and they are defined by three components in a three-dimensional Cartesian coordinate system. The components change with the orientation of the coordinate system, but the vector does not. Velocity, displacement, force, and a pole to a plane are examples of vectors. Tensors of rank 2, or second-order tensors, are often referred to as just tensors. They are represented by 9 numbers in a three-dimensional Cartesian coordinate system. The components change with the orientation of the coordinate system, but the tensor does not. Deformation and displacement gradients, permeability, stress, and strain are examples of second-order tensors. This slide summarizes second-order tensors. A second-order tensor T in index notation is written as T, I, J, with I and J varying from 1 to 2 to 3. You can think of the tensor as a 3 by 3 matrix. In asymmetric tensors, all 9 components of the tensor are different. In symmetric tensors, the components T, I, J are equal to the components T, J, I. For example, T12 is equal to T21. Symmetric tensors are therefore defined by just 6 components. Stress and strain are symmetric tensors. In antisymmetric tensors, the non-diagonal components T, I, J are equal to the components minus T, J, I. For example, T12 is equal to minus T21. Similar to vectors, tensors can be transformed as indicated by this equation. The transformation is more difficult than for a vector, but as we will see in class, it is easy to implement in computer code. Finally, symmetric tensors such as stress and strain have a special property. There is a particular orientation of the coordinate system for which the only non-zero components of the tensor are along the diagonal of the matrix. These are called the principal axes of the tensor. To learn more about these concepts, read these sections from Chapter 7 of Allmendinger et al. And answer these questions.